We're actually going to be doing two separate presentations at the same time today. Tim Gordo and I are going to be talking about the open source spectrometer, and then Nick's going to be talking about the embedded GUI. They sort of tie together, and we'll talk about that. So first we'll go over some basic spectrometers.
Yeah, so I've made fairly good progress on the actual prototype for the spectrometer. Right now we've been using a CNC machine to basically machine it in. I had one of the early prototypes in my pocket if anyone's interested afterwards. I've been using FreeCAD, and I recently broke AutoCAD Inventor, which is surprising. But the next step is to build an aluminum enclosure, which is going to be a little worse because I can't use contact cement anymore, and I'm going to have to use actual optics instead of doing what I have been doing, which is taking basically almost mylar film and then cutting curves into polycarbonate and then coating it so you get whatever mirror you need. But yeah, the next step is to make an aluminum enclosure, use professional or at least quantitative optics to account for losses in the system, and then make mirror profiles that are round so they can sort of just sit in if we're using those. And then the other step is to actually work with a detector. We've done some work on that, but it requires very strange voltage rails to make it work. It needs like 11 volts or something.
Yeah, at the end of last semester, we had the electronics basically functional, and we're right now sort of waiting on the optics part to be ready to refine the electronics chemistry with optics.
So then I'm going to go into what the actual design is. I think it's Cerny Turner. It's the cross version. There's a classic one, which you basically just lay these out in a horizontal fashion so it keeps bouncing back and forth. The advantage of this, as you can see, it's a big mess, but it's a small mess. It's a lot more compact, and then the advantage that I think that I've brought to it that a lot of commercial people don't, because they have the ability to make their own mirrors and grind them themselves, so they end up using really weird, like highly optimized focal lengths. And so instead of going for as high of an optimization as I could, I tried to use extremely standard components, so everything uses just like 50 millimeter focal length, which you can buy anywhere basically. And so what actually goes on is that you have your entrance slit, and you want it as small as possible because you want as small an image as possible, because everything here is basically going to be a copy of that image, and if you have just a big hole, everything's just going to be a mess on the detector. And so you take the imaging slit, and then you need it to be incident on the diffraction grating. They all have to be parallel, or else they'll all scatter in different directions from there. And so you need a mirror to collimate it. So they come in, they spread, and then they hit the grating parallel. And then from there, the physics of the diffraction grating means that every different wavelength goes off at a different angle. And so they reflect off the diffraction grating onto the second mirror. And the point of the second mirror is to focus all those individual wavelengths to a point. But because they're a spherical mirror, even parabolic mirrors do it. If you have two different sources hit them at different angles, they won't focus to the same point. If you use a spherical mirror, they focus to a curve, but it's not entirely noticeable. If you use a parabolic reflector, which is insanely much more expensive, they will focus to a line, but you can actually get a fairly decent optimization across all the wavelengths if you use pretty cheap spherical mirrors. So any questions? Anyone know what I'm talking about? Yes.
So those mirrors are slightly curved?
Yeah.
These two.
Yeah.
The diffraction grating is a reflective grating and is straight, not curved.
Yeah.
Some commercial designs use a curved diffraction grating. That ends up being a little more expensive.
Yeah. Mostly because if you have a plane grating, they just cut them. If you use one of the concave gratings, they have to optimize it so that none of the spacings and none of the rulings are, I guess, the same width apart. They're all optimized to.
And to give you an idea of scale,
image.
the diffraction gratings we're looking at using are around 600 lines per.
Yeah, 600 lines per millimeter. which gives you very broad range. If you use a lot of lines per millimeter, you get a larger separation of wavelengths, but it also decreases the range over which you can detect things, because you might be talking about you're spreading out like maybe a 300 nanometer range over like 20 or 30 degrees, whereas if you use something with lower separation, you don't get as good a resolution, but then all of a sudden you can be like 900 nanometers for the entire range of detection.
So you are questioning only the RGB of the distribution?
No, this is just to demonstrate, because I mean, red, blue, green, they're all kind of evenly spaced throughout the visible spectrum. The plan for this is to go from 350 to about 1100, so very, very deep blue.
We'll go from basically like a black light all the way through infrared.
Yeah.
It's the most commonly encountered spectrum and the most commonly used spectrum in lab exercises.
One more quick question. What kind of calibration does this require over time? Like, does it get out of whack a little bit?
Ideally, not much.
Yeah.
Most commercial spectrometers of a similar design, similar like optics bench layout, recommend a yearly calibration, but
That's just because they want
it's
you
just
to
a
check.
recommendation. I want to keep paying money.
So in
You probably
reality-
wouldn't see any drift. None of the components will do gradient page. If you were to drop it though, and something moved inside of that,
Okay.
would require it.
Which is a consideration that we're going to have to make.
So now for the electronics of the spectrometer. Originally we were considering using a microcontroller, a Stellaris M4 series. However, after working with it a bit, we decided it would make more sense to move towards something with more processing power, particularly if we're correcting for some of the optics imperfections in software. This also gives us the ability to do more complex things, like have an on-device graphical interface with touch. So what we're actually developing now is a small Linux computer that will fit on a circuit board less than 2 inches by 2 inches and can be embedded into another device. So this is completely prototyped at this point. It's based off an existing open source design, and we're about ready to do a first like prototype run, manufacturing run, to have a few to start actually playing.
Yeah, so what I've been working on is basically making the designs for that little prototype computer. And we're basing it off of a design by a company called Olimex that's based out of Bulgaria, I think, of all places. So we have one of their development boards that's basically the same circuit that we're going to be using in the same computer effectively, but we're taking that design and we've switched out a lot of components for manufacturability, using a lot of surface mount stuff rather than through-hole stuff, changing the power supply so you don't need quite as much supporting hardware off the board itself in terms of like USB connections and things like that. And getting the board designed as small as possible. And I think within the coming week, we'll be able to order our first prototype of that design and then hopefully be able to start playing with it.
What is the power supply need?
I'm sorry?
What is the power supply need? How much?
So the board we currently have, you can power either off a USB port, off another computer, or off of a 9-volt barrel jack. But for the purposes of our little tiny board, because it's going to be built inside of another device, we're just going to feed it power through a couple of pins, and we won't need the barrel jack or the USB port or any of that. Yeah.
Yes, in the last presentation, when I sort of introduced this idea, I said how it's not like Raspberry Pi. It's pretty similar though in terms of functionality. It basically has the same kind of processing power, the same kind of GPU on board, but we're eliminating most of the peripherals that you wouldn't really need if you're planning on using it to control some sort of embedded hardware.
It actually has more processing power. The Raspberry Pi is like 700 megahertz, and this is going to be a gigahertz.
Yeah, something like that.
And then this uses a Model 400 GPU instead of whatever video core proprietary thing. Yeah.
Okay, so I'm working on the software side of things. So basically what I'm doing is I'm working on the making a graphical interface for LCDs, both for spectrometer and vital. It's also kind of for general usage of people who want to make an interface. What we've accomplished so far, we got Debian successfully running on the chip. We started using Qt embedded, which I'll go into a little more. We've had some hardware complications. But we've got some hardware coming in, and after that, development should be really simple. Okay, so Qt Embedded is actually really cool. Basically, it's a framework for graphical applications, and it doesn't need to run with X or anything. So we don't actually need to run graphical Linux to have graphical applications, which saves a lot of memory and resource usage. And it runs in something called the frame buffer. The API is really good. You can run it, you can build it, and it'll run on Linux, Mac, your embedded hardware. So it's really nice to develop with. So here's a video. We've been having problems with LCD, but we were able to get this running in VGA. So this is running without graphical desktop at all. This is their one of their demo applications they have, Fluid Launcher.
That's the Olenex board there that we're currently testing software.
So here it's just demonstrating some of the capabilities you can do with Qt Embedded. This processor can run a graphical desktop. It won't run as smoothly. These applications ran pretty smoothly. They don't have a lot of overhead, so very snappy.
And once again, it's running all without X, so there is basically no overhead.
Most applications where you'd be using this hardware is going to be where you want a simple user interface. You might want some buttons or maybe a text input or something. Or it might just be something as simple as you want your device to be able to communicate with Ethernet, and it's more cost effective and much easier to develop for a small Linux system than to try and use Ethernet shields for an Arduino.
Sorry, assume Python can run in your embedded hardware.
Yes.
Yeah. So it has a lot of I/O pins, actually 40 or 60
Yeah, on
or
the order of
something
like
general I/O
48 I/O pins that you can just use any way you want.
Did you say Python, right? Yeah. Yes, Python can run on it.
Yeah. So
Okay.
well, I was going to
We're
get to
gonna-
it if you didn't
yeah.
interrupt me. I was going to say they can be talked to with any higher level language, and you can use it in place of like an Arduino or some smaller microcontroller without the need for that extra step between the two.
So here's some of the milestones that I've hit. A lot of it's just getting Debian set up and configured correctly. One of the problems we've had though is that the Debian build that we were able to get running on this is not able to work with the LCD, and all of the builds that they've had are hard coded for 512 megabytes of RAM, which is not what they say in the documentation. So even though we've been able to get all this stuff running, we still don't have communication with the LCD. We had to modify hardware requirements to accommodate that. Additionally, the LCD they sent us was cracked, which is great. So we've been talking to Svetlana from Bulgaria to deal with that. And so yeah, Olenex has been great with that. But after we get the new hardware, things should be running pretty smoothly. Part of also what I'm doing is documenting everything pretty closely. So part of what I'm doing is that hopefully people who are trying to replicate these projects can it's very closely documented so that it's easy for people to replicate what I'm doing basically. Just including all the resource links, code you're typing. So hopefully that will be useful to people.
But are they being from somewhere, or where, how do we get to this?
Well, right now this is Well, this is in the repository of the binaries we have. This is also in the subversion, but hopefully it'll be published somewhere that's accessible to people.
That's very good.
I guess final pending things that we need to do, get the LCD working, and then basically the design of the interfaces for stuff. So. Another thing is that the observatory says we're not doing anything, but we really are. So I guess it's not like in Google Code Subversion, but we are making commits. So don't believe what it says.
Thanks. Yeah.
And thanks to everyone, Sean, Sullivan, Morthy, Goldschmidt, RCOS people. So, any questions about any of the stuff we're working on? All right, thank you.